Hi, I'm Jared.
And I'm Tony.
And this is our final year project, LabLAN.
Within the Electrophotonics Laboratory at Monash, ultra-high capacity optical communication systems are researched. This is conducted with the use of state-of-the-art arbitrary waveform generators and oscilloscopes, among other devices. The lab also has access to over 40 kilometres of dark fibres present between Monash University, RMIT, and the University of Melbourne, where each location has its own specialised equipment to facilitate such experiments.
This project investigates the possibilities of a testbed to maximise the use of a suite of local and remote devices. The notion of an Internet of Things has recently surged in popularity, but its adoption in a laboratory environment is rare, let alone simple to set up and easy to use. Many of the measurements required for testing and experimentation are repetitive and cumbersome to execute. This requires many iterations and manual transfers between devices and computers, providing a clear candidate for automation. The ability to also remotely control and utilise equipment from any of the locations would catalyse collaborative research and discovery.
Access to an AWG and an oscilloscope were provided to explore the functionality of the project. Beginning with direct connection from a computer to a single device, a range of challenges and milestones were encountered. This included maintaining project version control, software encoding library incompatibility between and within devices, installations on varying system requirements, and more. But further features were explored and adapted to the testbed as they were met and overcome to discover the potential of LabLAN.
This solution is able to facilitate consistent communication from a computer to both an AWG and an oscilloscope. LabLAN is already being utilised to achieve a significant speed up in the delivery of research by allowing for fully automated experiments to run overnight without requiring periodic human interaction. Because of its relatively simple setup and use, it has also been integrated into the academic environment for student use while reducing the risk of damage to valuable equipment. A GUI implementation of LabLAN has been created on MATLAB for a more user-friendly experience, as well as individual coding instructions and commands for tested instruments, allowing for specific scripting and automation. Finally, LabLAN also enables access to devices on designated networks over long distances, fostering the possibility for collaborative efforts for connected research facilities.
The capabilities and benefits of LabLAN not only apply to Monash's electrophotonics lab, but any lab or field of research with high-powered and specially designated devices. Further recommendations include automating the setup and preparation for a general user, investigating more secure network connections and infrastructure, as well as the number and range of simultaneously connected devices to explore the full potential of the solution. Now, we will take a closer look at the project, including the goals, methodology, and inner workings of LabLAN.
The project began with us gaining an understanding of the existing systems and automation within the photonics lab. Bill had some software which was able to automate some devices such as the oscilloscopes, but other devices such as the AWG relied on onboard software that was cumbersome and inconvenient for automation.
This sketch by Bill from the early days of the project show his original vision for its outcome. The top diagram details the network mapping of the oscilloscope and the AWG connected through an Ethernet switch to a PC. The bottom diagram shows the theoretical remote connection to another lab, which we touch on later. Using this, we are able to visualize the way the devices will be connected and what infrastructure was needed to communicate with the AWG.
The top front panel is able to facilitate AWG communication over a network layer. However, it's very limiting in what sort of tasks it can achieve. Namely, for the experiments run in the photonics lab, we were required to be able to upload a custom waveform to the AWG, a task that is not possible with the existing implementation.
In our research, we didn't find many solutions that tackled the problem the way that we saw it. We did find that Nokia's Bell Labs were looking at something similar, but this required in-depth knowledge of operating systems and Linux. What we have were devices that run on Windows, and we needed MATLAB coding. So we sought a solution that connected these devices with Python and interface with MATLAB.
Python was chosen to work with MATLAB as it is a widely supported language with many libraries and online resources, giving us powerful, adaptable, and easy-to-use tools to achieve our goal. Now that we understood the problem at hand, our objective was to design and create a solution that maintained capability, flexibility, and low cost. With these in mind, we set a series of proof of concepts and milestones to reach in order to build towards our goal.
We began by interfacing with an instrument through Python's serial library. However, this proved inconvenient as it was very device specific for the connection. We then moved on to using PyVisa library in order to communicate with instruments in a more generalized manner. However, this introduced a problem that we were unable to communicate with the AWG since it was on the embedded PC's parallel bus. We got around this problem by using a combination of the soft front panel with our own software to facilitate the communication.
After some initial testing, we actually found that Bill's code generated numbers that was outside of the range for the function generator. Looking further into this, we found that the soft front panel actually normalized these values to be able to be generated. This meant that we had to incorporate this into our solution.
The MATLAB and Python layers are able to interface it with each other through MATLAB System Connect. MATLAB calls system and tells it the specific Python functions that are to be called and also passes it the arguments. It then receives back the arguments from the response based on the server.
After designing our Python infrastructure as the backbone for our project, we wanted to use MATLAB as the interface for the user. Taking the design of the soft front panel for the AWG, we designed a MATLAB app that allows the user to use the same features.
After showing our connection to a single AWG, we wanted to be able to integrate a number of devices in the photonics lab. For this, we set up a switch with static IPs on each of the devices. This allowed us to forward the correct ports to the correct devices, enabling us to be able to communicate with several devices from the one port.
This was further enhanced with specified Python scripts to allow direct control of the AWG and other devices through the Ethernet switch. Now that our primary objective of automated communication to the AWG was established and easy to use, we had the opportunity to flesh out the capabilities of LabLAN and truly prove the use case of fully automated remote experiments.
Because of the remote nature of our project, we were able to extend the usability of the instrumentation here beyond Clayton campus. So here we have the dark fibre connection between Monash Clayton campus and RMIT City. Here we have the TX and the RX lines, which facilitate the communication between campuses, and the signal is converted to Ethernet to be sent to the AWG.
So at the moment we have this computer connected via this Ethernet cable through to the dark fibre connections down to Monash at Clayton campus. On our computer at Clayton campus we have a script that is running, sending instructions. And we can see here on this computer it is receiving the instructions from Monash, and over here we can see the outputs being toggled.
With the visit to RMIT, not only was the automated aspect of LabLAN proven to be adaptable to other environments, but the remote and collaborative potential with other laboratories was unlocked. This now means that several real-time photonics experiments can be running simultaneously, both locally and remotely. And here, our final sketch shows the current network diagram of LabLAN.
Looking back at our project, all of our milestones helped us achieve our major goal of automating the process to use an oscilloscope and a function generator. Bill is already using this in his current research, as well as applying this in undergraduate classrooms.
Future development is still possible on our project, specifically with security. Our current project uses TCP, which sends plain text strings between the server and the client. Replacing this with something such as HTTPS, which uses certificates to encrypt the traffic, would be more secure. Also, it could be possible in the future to introduce more devices onto LabLAN by using serial communication on the server.
LabLAN could also be applicable to other schools of research such as chemistry or physics, and it depends really on the equipment that they have, whether they can use the PyVisa or PySerial libraries. So that would be something great to see LabLAN being applied to. As a team, we were able to work well to bring together our strengths and degrees for this project. We already had some knowledge of coding and time management and network understanding, but
this project taught us a lot about how to integrate different libraries together into one coherent production. We also spent a lot of time looking into manuals of the devices that we were interfacing with, and so it taught us a lot about how to be able to go through technical documentation and utilize that to achieve the project.